Hello and welcome to this video, which is 13th set of complex number problems. So in this video, we will solve problem number 121 to 130. And I have some feedback on my videos that I need to go a bit slow because I have received the feedback that I was going very fast. So I'll try to slow down, and also I will write solutions in more detail. I will not take shortcuts. So without further ado, let's get started. And as always, I'll say that when I am reading the problem, you should pause the video. And if you cannot solve the problem, then look at the solution and try to understand it. So problem 121 says that if Z1 and Z2 are complex numbers such that A into mod of Z1 is equal to B into mod of Z2, where A and B belong to the set of real numbers, then prove that A Z1 by B Z2 plus B Z2 by A Z1 lies on the segment -2, 2 of the real axis. So we let that the argument of Z1 is theta and argument of Z2 is theta plus alpha. So we can write A Z1 as A mod of Z1 into e to the power I theta. And similarly, denominator can be written as B mod of Z2 into e to the power I theta plus alpha. So you see that A into mod Z1 is equal to B into mod Z2. So we can cancel A into mod Z1 and B into mod Z2. So e to the power I theta by e to the power I theta plus alpha will be e to the power minus alpha. Similarly, we take reciprocal of what we have computed here, and we will have bz2 by az1 is equal to e to the power I alpha. Now we add these two, we get e to the power I alpha plus e to the power minus alpha. Now e to the power I alpha is nothing but cos alpha plus I sin alpha, and e to the power minus I alpha would be cos alpha minus I sin alpha. So when we add these two, the imaginary part, that is I sin alpha, will get cancelled, and the sum would be 2 cos alpha. Now the maximum and minimum values of cos alpha is 1 and minus 1. So maximum value of 2 cos alpha will be 2 and minimum value would be minus 2. So you see that it lies on the segment -2 and comma 2 of the real axis. Problem 122 says that if Z1, Z2, Z3 are roots of the equation Z cube plus 3 alpha Z square plus 3 beta Z plus gamma is equal to 0 such that they form an equilateral triangle, then prove that alpha square is equal to beta. So we are given that Z1, Z2, Z3 are roots of this equation, that is Z cube plus 3 alpha Z square plus 3 beta Z plus gamma. Now you know that if there are three roots alpha, beta, gamma of a cubic equation, then x minus alpha into x minus beta into x minus gamma is equal to 0. When you will multiply them, you will find that the equation is x cube minus alpha plus beta plus gamma into x square plus alpha beta plus beta gamma plus gamma alpha into x minus alpha beta gamma. So you see that here we will have Z1 plus Z2 plus Z3 is equal to minus 3 alpha, and Z1 Z2 plus Z2 Z3 plus Z3 Z1 is equal to 3 beta, and Z1 Z2 Z3 would be minus gamma. There is a missing minus sign here. So now we know the condition for a triangle to be equilateral is Z1 square plus Z2 square plus Z3 square is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. So we add 2 Z1 Z2 plus 2 Z2 Z3 plus 2 Z3 Z1 on both sides. So left hand side will become Z1 plus Z2 plus Z3 whole square is equal to 3 Z1 Z2 plus Z2 Z3 plus Z3 Z1. Now we substitute the value of Z1 Z2 Z3, that is minus 3 alpha. So left hand side will become 9 alpha square, and right hand side will be 3 into 3 beta. So we can say that alpha square is equal to beta. This minus sign is of no concern here because we are not having a term which includes Z1, Z2, Z3, so you can actually ignore that. You don't even need to write this. Problem 123 says that if Z1 square plus Z2 square plus 2Z1 Z2 cos theta is equal to 0, then prove that Z1 comma Z2, this should be Z2, and the origin form an isosceles triangle. So we are given that Z1 square plus Z2 square plus 2Z1 Z2 cos theta is equal to 0. So we divide both sides by Z2 square. So get Z1 by Z2 whole square plus 1 plus 2 Z1 by Z2 cos theta is equal to 0. Now this is a quadratic equation in Z1 by Z2. So the roots would be minus 2 cos theta plus minus square root of 4 cos square theta minus 1 by 2. We need to know quadratic equation to understand where this came from. So we have Z1 by Z2 is equal to minus cos theta plus minus I sin theta. That means modulus would be 1. So mod of Z1 by Z2 is equal to 1. That means mod of Z1 is equal to mod of Z2. That is mod of Z1 minus 0 is equal to mod of Z2 minus 0. And thus we can say that Z1, Z2, oh, this is the typo again. Z1, Z2 and the origin form an isosceles triangle. Problem 124 says that A, B and C represent Z1, Z2 and Z3 on origin plane. The circumcenter of this triangle lies on the origin. If the altitude AD meets circumcircle again at point P, then find the complex number representing P. So since origin is the circumcenter, we will have the line we draw from origin to Z1, Z2, Z3 will be all radius of the circumcircle, that is mod Z. So we square this, we get Z1 mod Z1 bar plus Z2 mod, Z1 bar, Z2 into Z2 bar, Z3 into Z3 bar, all equal to ZZ bar. Now AP will be perpendicular to BC because it is the altitude. Okay, so it will make an angle of 90 degrees. So we can write that Z minus Z1 by mod, Z bar minus Z1 bar is plus Z2 minus Z3 by Z2 bar minus Z3 bar is equal to 0. Now we write this Z bar as from here we calculate this Z1 bar by Z, this and this, and similarly Z2 bar we write this from these two as Z3 bar by Z. Okay. So this Z2 bar we have changed, and this should be Z2 actually, this shouldn't be Z, this is Z2, and this is Z1 bar is equal to ZZ bar. From there we can write ZZ1 bar by Z. Okay. Let me think, this should be Z1 bar. This is also wrong. This one should be Z1 bar by, hang on, Z bar. Yeah, Z1 bar by Z. And this is Z3 bar by Z2. So now we bring Z to the top, we bring Z2 to the top. We have this much. And then you solve this further. We will eventually get minus Z by Z1 minus Z2 by Z3 is equal to 0. So Z is equal to minus Z1 Z2 by Z3, which is the coordinate of P. If Z1 and Z2 are roots of the equation Z square plus PZ plus Q is equal to 0, where P and Q can be complex numbers. Let AB represent Z1, Z2 in the complex plane. If angle AOB is equal to alpha, which is not equal to 0, and OA is equal to OB, where O is the origin, then find P square. So we are given that OA is equal to OB. So that we can say that Z1 mod is equal to Z2 mod is equal to L. That is the length of or the modulus of OA and OB. Now we are given that AOB is equal to alpha. That means arc of Z1 is equal to alpha plus arc of Z2. So we can say that Z1 is equal to L e to the power I alpha plus R cos Z2. That is L into e to the power I R Z2 into e to the power I alpha. That is Z2 e to the power I alpha. Now Z1 Z2 is nothing but Q. That is Z2 square e to the power I alpha. Okay. This much is equal to Q. And Z1 plus Z2 is minus P. So this is equal to Z2 into 1 plus e to the power I alpha is equal to minus P. Now we substitute e to the power I alpha value from here, or rather, not substitute yet. So this e to the power I alpha is cos alpha plus I sin alpha. Now cos alpha plus 1 is 2 cos square alpha. And I sin alpha is 2 sin alpha by 2 cos alpha by 2. So we take out 2 cos alpha by 2 common. So inside bracket we will have cos alpha by 2 plus I sin alpha by 2, which is equal to e to the power e to the power I alpha by 2. So the left hand side becomes 2z2 cos alpha by 2 e to the power I alpha by 2 is equal to minus p. So we square both sides, we get p square is equal to 4z square cos square alpha by 2 into e to the power I alpha. Now we are given that q is equal to z square e to the power I alpha. So we substitute and we get p square is equal to 4q cos square alpha by 2. Problem 126 says that if real of z plus 4 by 2x plus minus 1 is equal to half, then prove that the locus of z is a straight line. It looks like it is 2x minus I. Okay. So we let z is equal to x plus iy. This is all typing mistake. So this becomes x plus 4 plus iy, and this becomes 2x plus I into 2y minus 1. This looks like wrong. Okay. This can be possible only if x is nothing but z. So it is z plus 4 by 2z minus 1. So it is 2z minus 1, or rather 2z minus I. It is 2z minus I. It's a huge typing mistake, because if this is 2z, not 2z minus I, this won't be 2x plus I 2y minus 1. So we let z is equal to x plus iy, and real of z plus 4 by 2z minus I would be x plus 4 plus iy by 2x plus I 2y minus 1. And then we multiply and divide with the complex conjugate of denominator like we always do. And that is equal to half. So then you compare the real part and you solve it, you will get 16x plus 2y minus 1 is equal to 0, which is equation of a straight line. Now, if you have not studied coordinate geometry, you would not know that this is equation of a straight line. So I will request you to study coordinate geometry to solve this. That's one of the problems with complex number, because it involves the concepts of coordinate geometry, quadratic equations, and trigonometry all together in one topic. So you need to be clear of all those topics to actually solve all the problems in complex numbers. Problem 127 says that if Z1, Z2, and Z3 are vertices of an equilateral triangle inscribed in the circle mod Z is equal to 2. If Z1, Z2, Z3 are in clockwise sense, then find Z2 and Z3. So since the circle is inscribed in mod Z is equal to 2, so center would be origin. Now Z1, Z2, Z3 are in clockwise direction, so Z2 would be Z1 e to the power minus I 120 degree, and Z3 would be Z2 into e to the power minus I 120 degree. So yeah. Now I think there is some missing information here. Yeah, Z1 should be 1 plus root 3i. It looks like there is again a typing mistake. Yeah, Z1 should be 1 plus root 3i. That should be given in the question. So once we have Z1, we can compute Z2, which would turn out to be 1 minus root 3i, and Z3 will be can be further computed, which will be minus 2. Problem 128 says that if Z1 is equal to a by 1 minus I, Z2 is equal to b by 2 plus I, Z3 is equal to a minus bi, where a and b are in set of real numbers, and Z1 minus Z2 is equal to 1, then find the centroid of the triangle formed by Z1, Z2, and Z3. So what we do is we rationalize by multiplying with complex conjugate. We get Z1 is equal to a plus IA by 2, Z2 is equal to B by 2I, which is 2B minus IB by 5. Now Z1 minus Z2 is equal to 1, so we subtract Z1 and Z2. We get 5A plus I5A minus 4B plus I2B is equal to 10. Now you compare real and imaginary parts, you will get 5A minus 4B is equal to 10 and 5A plus 2B is equal to 10. These are two unknowns, A and B, and two equations. So you can solve this. You will get A is equal to 2 by 3 and B is equal to minus 5 by 3. And centroid is Z1 plus Z2 by Z plus Z3 by 3. So substitute for A and B for Z1, Z2 and Z3. Z3 is given A minus BI. So you substitute that and you have A, B, and then you find this as final centroid. Problem 129 says that if lambda is a real number, given lambda is a real number, it should not be if. If the origin and the non-real roots of 2z square plus 2z plus lambda is equal to 0, form three vertices of an equilateral triangle in the Argand plane, then find lambda. So from the quadratic equation, we can say that Z1 plus Z2 is equal to minus 1 and Z1, Z2 is equal to lambda by 2. Now we have to form an equilateral triangle from 0, Z1 and Z2. So we can say that Z1 into Z2 plus Z2 into 0 plus Z1 into 0 is equal to Z1 square plus Z2 square plus 0 square. Now we have Z1, Z2 is equal to Z1 square plus Z2 square. So we add 2 Z1, Z2 both sides. So we get Z1 plus Z2 whole square is equal to 3 Z1, Z2. Now we substitute the values for Z1 plus Z2 and Z1, Z2. We get lambda as 2 by 3. Problem 130 says that if A, B, C and U, V, W are complex numbers such that C is equal to 1 minus R into A plus RB and W is equal to 1 minus R into U plus RB, where R is a complex number, then prove that triangles are similar. It's a very simple question actually. I think it is one of the easiest problems in this set. So we let ABC represent ABC, and that is capital ABC represent small ABC, and capital UVW represent small UVW. So we can write that AB is equal to B minus C, BC is equal to C minus B, and then we put the value of C. We get A minus B into 1 minus R, and CA is equal to A minus C, which is equal to R into A minus B. Similarly, we get the values of UV, VW, and WU. And then you will find that AB by UV is equal to BC by VW is equal to CA by WU. And all these values would be similar. All these values would be same. And thus you can say that the triangles are similar. So how do you arrive at this? So AB by UV is B minus C by V minus U. And this is A minus B by U minus V. And this is A minus B by U minus V. This should be B minus A. This shouldn't be B minus A. This is B minus A. Okay. So see that all the values turn out to be A minus B by U minus V. So that is the common value. And since the ratio of sides of two triangles are equal, we can say that triangles are similar. So with this, we come to the end of 13th set of problem. Let me know, do you like the slower speed or do you like the faster speed of explaining the problems? Do let me know that in the comments. And I hope that you have enjoyed this video and found it useful. If so, please subscribe to the channel and like the video, because that motivates me to make more videos like this. And also other students like you will benefit from this video, because if you like and subscribe to the channel, then the video will reach to more students. That is how YouTube algorithms work. And I hope that you have been enjoying this series so far. I'll see you in the next video. Thanks a lot for watching. Enjoy.